Okay, well, welcome to another edition of Experience OC. My name's Kevin Douglas. I'm a professor in the Physics and Astronomy department at the college, and I really am happy to be able to tell you about what we do at the college. Physics is one of the core science fields, and uh, when I was in high school, I had some really great physics teachers, and I think that's one of the reasons I enjoyed it so much. I went to Penn High, Penticton Senior Secondary, so I am from the Okanagan. I grew up here and everything. And my grade 12 physics teacher, Mr. Stelluti, had this wonderful idea about how physics can be viewed in the grand scheme of science. And he said, science is like a tree, and there's all these branches on that tree. And, the trunk of that tree is basically physics. In other words, physics is central. It's essential to all the other sciences out there, not just science, but also the, technology and engineering kind of offshoots of it as well. So, and I especially liked how he said about this, that underneath that, the roots of that tree are philosophy. Mathematics and philosophy are kind of the basis of thought, and physics is it's an aim to understand everything about the universe. So you can think of it as a highly challenging, highly complex field, but the rewards are worth it in many of our opinions. So I do want to talk a bit about how cool physics is. This is an Experience OC, so I also have a bit of a lecture plan, the kind of lecture that you might take if you were at a college course specifically on astronomy. I'm an astronomer, been doing astronomy since I got out of high school, basically. So if you're thinking about physics and what is it, why do I have to take it, that sort of thing, I think it's just it's the way to understand things better. If you can it's not that the more physics you take, the smarter you'll be. It's more that the better you understand what you're learning, the better you'll be able to understand anything else you ever learn. Okay, so the skills you learn by taking a physics course include solving equations and calculating numbers, but it's much, much more than that. It's about understanding concepts and truly understanding things at its most fundamental level. So I always tell my students, physics seems hard because its ultimate goal is to understand everything. If you're trying to understand everything, clearly it's a big job, and no one single person can do it. Nobody is born a physicist. Just a little bit about what you might expect at Okanagan College then, if you're considering taking some courses in our department. As I said before, it's a core science course. You could pair that with chemistry, biology, and mathematics. There's also computer science, etc. here at the college. As far as our department goes, across the valley, we have 8 permanent faculty members. And I will guarantee you that if you take a course from any of them, you'll get a sense of how passionate we are about physics, and especially how much we want you to enjoy, make sense of all your physics. Out of those 8 faculty members, 4 of us do come from an astrophysics background, including myself. Some of us grew up in the Okanagan too, not just myself, but others as well. But amongst us, we have a very diverse background of research topics. One of us has a degree in physical oceanography, also biophysics, mathematics, you name it. We have some specialty abilities with that. Now, one thing that you might think about, what is the benefit to taking a college level course versus going to university? And you've probably heard this before many times, but it's absolutely true that at universities, your first year courses, not just physics, but physics, chemistry, biology, math, etc., are usually in the hundreds of students per class. And so it's very difficult to make any kind of connection with your professors, and that's always a valuable thing to do. Here at Okanagan College, our first year class numbers are around 30 students per class. And most of us make it a point to get to know our students as best as we can. And so that's something that can be beneficial, especially when you're, trying to identify what it is you want to do going forward. So we do 2 years of courses. You might think about the exposure to research as well. Usually after your second year, there's not many opportunities for jobs, say, with professors until you get to your third or fourth year anyway. So another good reason to think about 2 years at a college is just, there's so many reasons, including the lower tuition costs, the ability to stay where you are if you're not living in a big city, etc. So Okanagan College is totally equipped to handle first-year physics offerings for students going into any scientific field, also engineering. I'll just talk about the two main streams we have. We have 2 courses in the first year for what you might call the life science. Maybe you want to go into the biology, chemistry, pharmacology fields. That's physics 112 and 122. If you look at our calendar, they're listed as algebra-based physics. And then we have other courses which are called calculus-based physics. It's not that it's all taught with calculus, it's more that it's just saying that this is targeted towards students who are going to go on in the more physical science fields, a field that has physics in the name, maybe like geophysics, biophysics, astrophysics. So physics 111 and physics 121 are kind of geared toward those students heading on in the physical science direction. And that can include engineering. There's a first year engineering curriculum that if you take those courses here at the college, you're ready to go on to engineering at university. So besides the first year level, we have several second year physics courses. Right now I'm teaching a modern physics class, which is a lot of fun. We talk about subatomic physics and cosmology, all kinds of cool things, Einstein's theory of special relativity. And we are a Department of Physics and Astronomy, so we do teach a lot of astronomy. We've got some first year kind of core, what is astronomy all about science courses. We also have a couple of specialized second year astronomy courses as well, one of which is on astrobiology, life in the universe, if you like. And another one is kind of the history of science from an astronomical point of view. Very rich topic. Just wanted to show you a picture of the observatory that I mentioned earlier. Down the road from you, wherever you might be in the Okanagan, there's the White Lake Observatory, otherwise known as the Dominion Radio Astrophysical Observatory. I've worked there in the past. Other people teaching at this college in our department have also worked there. And we do try to get students out there. This is a field trip that we did one April when it was nice and sunny like it is today. And you get to meet some of the scientists who work there and learn what it is they do at this place. And so it's a great place to get exposure to world-class science, physics and engineering especially, that's being done right here in the Okanagan. So if I didn't mention this already, I did grow up right near this place. I would say this place basically inspired me to pursue a career in radio astronomy. And sure enough, that's what I did as my research while I was a university student. And for the intervening years, about close to 20 years in the field before I started working here at the college. And I still maintain a good relationship research-wise with some of the people at this observatory. Now, the next few slides, basically the rest of my talk, is meant to be like an experience of what it might be like to take a class at the college. Some of these words I say might be something you're not too familiar with, but I want you to just sort of get a sense of what it might feel like to attend a physics lecture and sort of learn about a very interesting topic. So in fact, this topic of cosmology, it's touched on in astronomy. The course I'm teaching right now, we're going to talk about cosmology basically tomorrow. I have a whole lecture on cosmology. So some of these things I talk about today are very much the material that I teach to my class. So cosmology is a field of physics, especially astrophysics, that tries to understand the whole history of the universe, not just what happened, but the reasons why they happened, what physical processes dominated, etc. So it's an incredibly complicated field, but there's so much to learn, and it's one of those fields that we're still at the forefront of things. It's not completely understood yet. There's so much more to do with it. So if you've heard about the Big Bang Theory and how the universe was created, this is the kind of material that cosmology is all about. There are physical theories about how the universe was born and how it evolved. And the big thing about science is you can't just theorize and not come up with ideas to prove those theories. Any theory that's worth proving has to have observations that back it up. So I'll sort of walk you through the theory first, and then near the end talk about what observations exist to prove these ideas. So the Big Bang is sort of the idea that the universe began as an explosion at a single point in space. And from that point in space, everything else evolved outward from there. It's very different from theories which said the universe had always existed and was a steady state kind of entity. And again, observations show that that's simply not true. The universe had a beginning and it has an age. Right now, the universe is thought to be about 13.7 billion years old. But over its history, cosmologists have sort of pieced together evidence of how things evolved with some so-called epochs or eras throughout that. So in my little talk, I'll walk you through these different epochs. At the very beginning, the time scales are so extremely short that it's highly uncertain what really happened, and it's mostly theory. The farther back in time you go, clearly the harder it is to prove all of this. But very shortly after the Big Bang, there were these quantum fluctuations that sort of set the stage for everything else that happened beyond that. That includes something called inflation, but also just the separation of all the forces of the universe and what separated matter from antimatter and the radiation profile of the universe as well. So when we're talking about shortly after, we're talking the first few seconds after the Big Bang. The next main era or epoch is what we call the radiation-dominated era. You could say that's around 400,000 years long. Radiation-dominated basically means that it was really hot, and light photons were more dominant in terms of the energy density of the universe than any of the matter that was in existence. And all the matter was there at the beginning. The universe hasn't been creating new matter during its lifetime. A big part of this is the so-called Big Bang nucleosynthesis. So if you've ever heard of a book, for example, called The First 3 Minutes, what it talks about is setting the stage for this thing called nucleosynthesis to take place. So I will explain this topic of nucleosynthesis. Then after the radiation-dominated era, the universe expanded to a volume where the temperature dropped enough that photons and light became less dominant than matter. So suddenly what really was the driving force of the universe's expansion and evolution is matter. Think of protons, neutrons, electrons, the building blocks of everything else. Suddenly that became the most important piece of the universe, if you like. So for the next 8 billion years or so, you could say that in this matter-dominated era, the universe took its what form it has now. Before the evolution of stars, though, we had a period of time which was called the Dark Ages. In other words, nothing was producing light yet. Okay, atoms still had to form, and in order to get light, we had to build things that give off light. In other words, stars. So the Dark Ages were a time where no photons were being produced. Eventually, atoms formed, and that's an event or epoch called recombination. So remember, atoms are bound systems of protons, neutrons, and electrons. Before recombination, you could think of all those particles as a big plasma or soup of unformed atoms, just the building blocks, but they weren't stable atoms yet. Eventually, those atoms had to collect together to make molecules and build, things like stars, galaxies, planets, life, etc. So that's a long time for all of that to happen. And something that's part of that evolution is the most recent 5 billion years. We're now in an era called the dark energy dominated era. So I'll talk a bit about what that means. Basically, it means that the universe has expanded for 13.7 billion years. But it turns out that in the most recent 5 billion years, that expansion rate is increasing. And that's kind of a mystery, because you think all the gravity in the universe should eventually slow that down. But there's some kind of anti-gravity force that is actually helping the universe expand faster than it did during the regular evolution of the universe. So in a class, we try to draw pictures that explain what's going on here. So I'm not going to belabor everything except to sort of show this, this illustration sort of gives you an idea that at the very beginning of the universe, there was just a very tiny point. And that point immediately greatly inflated to a very large volume. And for most of the rest of that time, that volume steadily increased in size. Although in the most recent 5 billion years, it's actually getting a little faster. So you can imagine this volume flaring out a bit. But you can see in the early stages, they're showing you that it's really hot, and you have this plasma of things like electrons, protons, neutrons, and a few actual nuclei like helium forming. But at this point of recombination, the universe kind of goes dark. We have the cosmic microwave background, which is something we can detect in order to prove that that sort of freeze out happened. But in the next prevailing time, there's no new source of light being made until about 400 million years, when the first stars will form. So that's what we call reionization, because ionization means, the giving off of high energy processes, including giving off of light. So from those stars, early galaxies formed. Some of those are called quasars. Galaxies like our own Milky Way formed, and so that's a lot of evolution over those billions of years. In those stellar systems, we also have to form planets, and there's probably a lot of planets that are as yet undetected. In the early universe, we're talking about, theorists try to go back as far as they can, but there are problems with singularities. A singularity is like a region of size 0. And so when you try to divide by 0, you get really big problems in math. So we're trying to say, how far back can we go to the beginning of the universe? We can't know what happened at time 0, but how much after time 0 can we start to formulate our theories? And it's pretty interesting that you can get at these numbers simply by unifying the main physical theories we have. You might have heard of grand unified theories where they try to combine all the physics there is about gravity, electromagnetism, nuclear forces, quantum physics, etc. So as you'll see in physics as you go forward, there are these things in physics called fundamental constants. Three of them come from the three sort of main fields of physics you can think of, which could be, gravity or mechanics. You've got capital G is Newton's gravitational constant, and it has these units in the meters, kilograms, and seconds, or MKS units. Also in electromagnetism, the speed of light is a constant that I have my students memorize as 299792458 meters per second. That's the speed of light in a vacuum, and nothing can go faster than that. No matter can travel faster than the speed of light. Another interesting constant is called Planck's constant, or there's a version of it called Planck's reduced constant, which is an H with a little bar through it. And again, it has some units in the meters, kilograms, and seconds. It's a unit of angular momentum. And so if you unify the universe in its theories of gravity, electromagnetism, and quantum physics, you can derive the size scales or the time scales, etc., of the universe back in the early days. So these are called Planck units because Planck's constant is needed to form them. But if you play around with those constants and their units, you can take the square root of h bar g over c to the fifth, and that quantity has units of time. And the time you get from that, called the Planck time, is this extremely short interval of about 5.4 times 10 to the minus 44 seconds. In other words, that's probably the shortest timescale after the Big Bang that we can actually think of formulating a physical theory. We can't go any earlier than that. But that's basically a decimal place and about 43 zeros and then a 5. So that's a really, really short amount of time. And for a beam of light to travel across the universe in a Planck time, you can get something called the Planck length. So you take the Planck time multiplied by the speed of light, and you get the size of the universe, if you like, after that time scale passed. So again, it's an extremely small number. But again, what we now have is a universe that is, maybe 10 to the 15, 18, 21, who knows, meters across. So think of this as a theorist's lower limit in terms of how far back we can go in time. From that, we can talk about a lot of theories about what the universe went through during all of these epochs. I'm going to go somewhat quickly through all these slides because you don't need to worry about the details. I'd say, for example, this one shows the temperature of the universe as a function of time. And you can just see these temperatures are ridiculously high early on, but they steadily decrease to now. Now the universe might have some kind of temperature around maybe 3 kelvins. A Kelvin is a unit of absolute temperature. Zoe, you asked about the Planck length regulating string theory. That's absolutely correct. String theory and the membrane theory that goes around with it is very much constrained by trying to figure out the tiny scales of the universe. So yes, string theory is it's even too complicated for maybe undergrad physics, but it's a very cool topic. There's a few other important things you could talk about, like quarks and neutrinos. Again, these are things you learn about what they are. They are fundamental pieces of the universe, and they make up everything else. Click. Again, I sort of talked about separation of fundamental forces. So again, you go back in time, all the forces of the universe could have been unified. Gravity, electromagnetic force, and these things called the strong and weak force, which are only felt by things inside atoms. At one point in time, those were all one unified force. But as the universe expanded, cooled, the strength and those properties of those forces actually separated. And so gravity is now the hardest thing to unify with the other three. Just one quick slide about inflation, because if you take the size of the universe now and you extrapolate it back in time, you would actually predict the universe to be much larger than a Planck length. And that's problematic because it simply wouldn't be able to have a temperature hot enough to create things like the helium and other early atoms. So quite early in the formation of the Big Bang Theory, it became clear that to explain what we see now, there's this very short timescale inflationary epoch of the universe. And so basically, in an extremely short amount of time, the universe grew in size to a rather large size, after which it expanded more or less quite at a constant rate. Although again, more recently, it started to expand again. In terms of nucleosynthesis, let's see another chat. Zoe asks, the nuclear weak force and electromagnetism both stem from electroweak theory. You've got that right too. Electroweak theory is something that came out in the 1960s or so. And again, it's sort of these cosmologists going back in time to figure out how these things all work. So again, you know these words already, that's fantastic. It means you're ready to perhaps learn about leptons and quarks and all these cool particles. I love this slide because it sort of shows how the universe evolved in a more chemical way. Again, there's a book called The First 3 Minutes. And the idea is after the first 3 minutes, the temperature cooled to about 1 billion degrees. Okay, 1 billion degrees is still extremely hot. But before, in hotter temperatures than that, the universe is mostly protons and neutrons and electrons and almost nothing else. But once you cool to some temperature, like 1 billion degrees, you can start to invoke chemistry. And chemistry is a huge field of science as well. You can start to put 2 protons together and you get something called deuterium. That's what this 2H is. You can form tritium. You can form isotopes of helium and lithium and beryllium. But most importantly, you start to form helium, a stable isotope of helium called helium-4. And so once that happened, the whole rest of the evolution of the universe was possible, because you can think of, in terms of what the building blocks of matter are, helium and hydrogen are the building blocks of every other chemical that comes with it. So a lot of these neutrons, you see this blue line of neutrons starting to drop steadily. Well, that's because those neutrons are being used up to build all the chemical elements of the universe. So that's what we mean by nucleosynthesis. These are the nuclei of atoms. They're not the atoms yet, because they haven't trapped any electrons in stable orbits. But now we have nuclei from which we can start to build the chemistry of the universe. And you can assume as these temperatures get cooler and cooler, the chemical pathways will build up and up. I wanted to talk about now the transition from a radiation-dominated universe to a matter-dominated universe. Again, that mostly happens because the universe cools to some temperature below which photons have less, let's say, power or energy density in them than do atoms. And that happens at a temperature of about 10,000 kelvins. You can see this 10 to the 4. And that's pretty interesting because that's very much the temperature that it takes to sort of turn all the hydrogen atoms into bare nuclei. You basically ionize all the protons and electrons. You take away hydrogen atoms and they become bare protons. But at colder temperatures than that, you can actually start to form atoms. So as the universe cools, we move from this radiation-dominated era to a matter-dominated era. And so shortly after, shortly I say, but it's almost a million years or so, from the formation of, what do we call it? From the nucleosynthesis and the formation of nuclei, suddenly we have a temperature at which we can form stable atoms. And that's the first step towards forming stars, galaxies, planets, people, everything. So you can look at it as a temperature effect, or you can also look at it as what's called a mass density effect. I kind of prefer to call it an energy density effect, and you can follow these curves. You can say in the early universe, radiation dominates because the radiation line is higher. It has more energy per unit of volume of all the particles in the universe. Matter is there too, but it just has a different slope. But when those two things intersect, we suddenly join the matter-dominated part of the universe. But something we didn't know about until maybe about 20 years ago was that there was this mysterious dark energy line at the bottom here, this green one, all along. And suddenly, this is on this logarithmic scale, this point where the blue and green lines cross was about 5 billion years ago. And that's telling us at that point, something else other than matter took over in terms of what dominated the universe's evolution. It's given the name dark energy. It's got this capital lambda subscript. That's from Einstein's theory of general relativity about the so-called cosmological constant. And I look at it just like anti-gravity. It's something that opposes the gravitational attraction of everything to come together. It's the thing that helps the universe expand despite gravity. So in the last 5 billion years, which looks like a small amount of time on this logarithmic scale, we are in a different kind of realm in terms of how the evolution of the universe is taking place. It's still mysterious, though. Nobody really understands what's going on fully. But I like this diagram in terms of how it tries to illustrate that. Again, at the left side of the screen here, we have a big bang. We have a huge explosion, some quantum fluctuations followed by a very rapid inflation. 380,000 years later, we have the beginning of the Dark Ages. And this is what is sort of thought of as the era of the cosmic microwave background, is like a relic fossil of the start of the Dark Ages. And then after these Dark Ages, we can form atoms, stars, etc. And so you can see a lot of time over which the universe expanded at a relatively steady rate. But you can see this cone is widening out now. And that's to illustrate that we're now in a dark energy accelerated expansion era of our universe. And so, again, this is all theory of how the universe has evolved, but you can think that all of these different things we've been talking about should have some signature. The light or something about these events should be measurable. And so I will spend a little bit of time talking about these, some of the observational proof we have of all these cosmological effects. One of them is called the cosmic microwave background, which I hope some of you have heard about. This is a picture taken by a space telescope called the Planck satellite. This is not a picture of the microwave background itself. It's a picture of the anisotropy of that background. So I'll talk about what that means in a moment. But basically it's taking the whole universe's radiation signal, and if you subtract off the average, you get these little fluctuations. And so these little fluctuations have a great cosmological value. But the fact that these fluctuations are so small compared to the average is another proof of how the Big Bang theory successfully explains the evolution of the early universe. So the CMB, or cosmic microwave background, is said to be a fossil record of the epoch of recombination. In other words, when the radiation and matter separated more, when we turned into the matter-dominated era, photons kind of leaked out, and so this is a fossil record of the universe at that stage. Within that fossil record, though, is what's called an anisotropy, okay? There's structural information about the size scales of the quantum fluctuations and the inflationary behavior of the universe at the very beginning. So sometime in that early stage, a lot of the matter and antimatter produced at the Big Bang sort of annihilated, and that's why there were so many photons there. But there was some tiny, tiny imbalance of more matter than antimatter. And because of that, we have the universe we have now. But because of those little tiny mismatches in things on very tiny scales, we have an anisotropic cosmic microwave background. Isotropic means perfectly the same everywhere you look. So anisotropic means that it's not exactly the same everywhere you look, but it is the same with like 1 part in 10,000. So it's incredibly smooth, except that those anisotropies can also tell us about cosmological things. When the universe was going through these fluctuations, we had these things called baryonic acoustic oscillations. So baryonic just means made of protons and neutrons, mostly like ordinary matter. It's called baryonic. Acoustic just means that these fluctuations propagated at the speed of sound. Okay, so they're not sound waves, but they were sound waves through a plasma, if you like. But I'm going to call them BAOs as we go forward, because again, these objects or these structures have been measured, and they tell us about how the universe evolved. So it's actually another feather in the cap, if you like, of cosmology, that these baryonic acoustic oscillations correctly match the theory of how the universe evolved. I say they have a predicted size scale of about 1 degree on the sky. Okay, the full moon is 1/2 degree. So on the sky, there are little, back in time oscillations about the size of the full moon. And the thing about these BAOs is that they should keep that size scale over all time, because they are oscillating, or they're governed by the dark energy parameter. And you can see this dark energy parameter is flat. It doesn't change over time. Whereas radiation and matter, they care about how big the universe is in terms of how much strength they have. Dark energy doesn't care. It's mysterious. But these baryonic acoustic oscillations should keep their same size scale for all time. And these BAOs are being measured at the DRAO, the observatory here in the Okanagan. You may have heard about the CHIME telescope that they built there within the last few years. It was built as a cosmology telescope, and one of the main reasons it was built was to measure these BAOs and to confirm that dark energy behaves the way we think it does. It's going to win a Nobel Prize someday if it proves correct, I think. Back to the cosmic microwave background. This was done with a satellite, measuring the radiation temperature of the universe in all directions. The problem with that is that the galaxy is moving through the universe, and the solar system is moving through the galaxy. So there's something called a Doppler shift that has to be subtracted. So if you didn't know about that, you'd look at this and say, wow, the universe has this bipolar look to it. It's hot in one area and cold in another. But that's just not right. We have to remove this. This is a motion-induced effect. So we know how the universe, or we know how we move through the universe. So once we subtract this off, what you would get on this scale is a perfectly smooth oval. Basically, you'd say this temperature is exactly the same everywhere we look on this scale, because we're moving a scale of, let's say, a 20th of a degree of temperature or something. So when you subtract this off, you subtract the Doppler shift, and then you get the actual curve of the black body curve of the cosmic microwave background. And you get a temperature of about 2.725 degrees. Again, this is in Kelvin units, which are absolute temperature units. And all these squares show that the data prove that the universe is smooth with a constant temperature of 2.725 degrees everywhere you look, in every single direction. And that is a relic, a predicted relic of the Big Bang, and especially of the recombination era. Now, if you take that oval and you subtract off the number 2.725, you should get a 0 plus or minus the leftovers. The leftovers is what we call that anisotropy. And so again, that's what you get this so-called anisotropy picture of. But remember, these are small little temperature fluctuations that are left over after you've subtracted most of the signal. You can see that these are in the micro Kelvin range now. And so, 0 is perfect green, and a number that, like the reddest part here, is something like 2.7252 degrees. And the coolest part might be 2.7248 degrees. So that's an incredibly tight fit of temperature. But these oscillations, these anisotropies in this picture, are of interest to cosmologists. Cosmologists will look at this and say, okay, the size scale of these little structures tells me about the BAOs and what the universe was like as it was expanding during the radiation-dominated era. So you'll just have to take my word for it, but the average size scale of all these little blobs is 1 square degree on the sky. That's a prediction of the Big Bang, and it's also true in terms of what the data show. So this is something called a power spectrum. It's kind of a complicated graph, but what I want you to see is at the top, 1 degree is right about here in the middle, and the red line is a prediction. The red line says the universe should have most of its structure on 1 degree size scales, with a few blips at other scales. And the little dashes are the data from all the cosmology projects. So again, the data and the theory line up perfectly, telling us that the Big Bang theory as we understand it is correct. It's hard to believe that we're learning this simply by pointing telescopes and antenna up in the sky. I always like to say to students, think about how in many sciences you get to touch what you're working on. In astrophysics, it's quite strange because most of the time you're just trusting the light that comes from those objects. And that light is so precious because it tells you everything about what's going on. What's cool is that this is not, this is the end of my story, but it's not the end of the story as in terms of what's going on now. Okay, there are so many projects in cosmology and other areas of physics that smart people need to know about and get involved in. In terms of cosmology, or this story of the universe, I would say that the epoch of reionization, also called cosmic dawn in a lot of publications now, In other words, the time when the stars turned back on, the search for the epoch of reionization is being done by every industrial country has some kind of epoch of reionization project underway, and they need more scientists to work with that data. Also, just the instruments that are being developed for next generation science is just mind-bogglingly important, and I think there's truly there's going to be a need for a lot of smart scientists to work on these projects. So not just telescopes, but other kind of detectors to find cosmic signals from the universe. Again, very important areas of physics. You might have just heard just this past week that new physics was being discovered by the Fermi project, Fermi Labs down in Illinois. Okay, so there's all kinds of still cutting edge research to be done. As I mentioned before, the CHIME telescope here in the Okanagan Valley is going to be one of the main things that determine whether these baryonic acoustic oscillations confirm what we think about dark energy, but the data won't be ready for about 5 to 6 years. So we need some people now to start their degrees so that in 5 years they will be able to jump in and use that data. In the meantime, while it's collecting all that data, it's also become an extremely valuable detector of so-called fast radio bursts. So again, if you keep an eye on science in Canada, these fast radio bursts are something that the CHIME telescope is getting a lot of press about. So I'm a radio astronomer, so I'm kind of biased towards those radio type signals. But as you may know, the Hubble Space Telescope has a successor coming down. Someday it'll get launched, hopefully this decade sometime, called the James Webb Space Telescope. It will completely revolutionize cosmology in terms of what we can do at, let's say, infrared, optical, and ultraviolet wavelengths. It's just going to be extremely powerful. Also in the field of particle physics, something that Canada is a world leader in, many Nobel Prizes. They're building detectors that will understand neutrinos better. Over in Sudbury, Ontario, there's a neutrino observatory that has won all kinds of accolades for the research they do. So I've talked a bit about the current state of what we know, but I hope you understand that there's so much more that we don't know yet, and we're desperate for more people to get into physics so that you can help us solve all these new mysteries. I'm going to stop there. Thank you for listening, and I'd be happy to answer any questions you might have or any more comments you might have about what you've heard tonight.